Before you watch this video on scientific notation, make sure you have already seen the video over the significant figures, the Sig Fig video, because a lot of the things that make scientific notation different in chemistry is just the application of significant figures. So, scientific notation is just a way to represent a number, and it's usually used in science because a lot of our values in science have a very large value or have a very small value. And so, if I have a number that looks like this, well, more traditionally like this, 532,000, I can represent this number using scientific notation by writing 5.32 times 10 to the fifth power. Basically, what this means is you're going to take 5.32 and multiply it by 10 5 times, times 10, times 10, times 10, times 10, times 10. I know you've learned about scientific notation in the past, so I'm just going to, teach it to you again as if you've never seen it before. So scientific notation has this format that looks like this. You might remember hearing about the scientific notation in the Sig Fig video because anything that comes before the X, anything that's part of the mantissa, is going to be considered for Sig Figs. A Sig Fig is the numbers that are significant to a measurement. So M is the mantissa. This number should be in a single integer less than 10. So you should have one number in front of the decimal. We have a times 10 format, and then we have an exponent that can be any integer, either positive or negative. So here is an example of how scientific notation is important to us. This is the mass of a proton. This is the mass of an electron. Can you imagine when scientists were transferring data from one person to another through history, there is that opportunity to miss a zero or a set of three zeros. So scientific notation is a way that we can help preserve numbers like this with few error. So that is one good reason why scientific notation is useful for us to write the values for objects that are very small in science. This is Avogadro's number. Avogadro's number is one that we use quite a bit in the school year, and if we were going to represent this using scientific notation, we could represent it like this: 6.02 times 10 to the 23rd power. I actually would like to have removed that decimal there, but just ignore that. So this is another example. We have the diameter of the sun being 1,392,000 kilometers, and we also have the density of the sun. So with these two measurements, if you were to convert them into scientific notation, here is the explanation to do that. We would want to take its natural decimal place. So this is the diameter of the sun. We want to take its natural decimal place, and we want to think about where the decimal should be. The decimal should point to a factor that's going to produce a number between 1 and 10. So remember how I said you want to have one number in front of the decimal? We are eventually going to be moving our decimal place from here to here. So we can count how many times it would take to move there. It's going to take 1, 2, 3, 4, 5, 6 jumps to move there. And remember, we're multiplying the value times 10 6 times to do that. So in this example, we have the decimal moving 6 times to the left. In this example, we have the decimal moving 8 times, to the right. And watch how we can represent the scientific notation for each answer. Anytime the decimal is moved to the left, or it's the original value of the number is greater than 1, okay, so this is a very large value, then we are going to have a positive exponent. Anytime we have a number where the value of the number is less than 1, we are going to have a negative exponent. I'll explain that a little bit better in other slides. So you should only have one non-zero number to the left of the decimal. If the value is greater than 1, the exponent is going to be positive. And then if the value of the original number without the scientific notation is less than 1, the exponent is going to be negative. So the number of sig figs have to stay the same from from to and from long form or scientific notation form. So let me go ahead and show you an example. If I have a number that looks like this, if we're going to convert this number into scientific notation, the first thing I want to just make quick note of is how many sig figs there are in this number. I have 1, 2, 3, 4, 5, 6, 7. 7 significant figures, 7 numbers that are significant to the measurement of whatever object this number represents, whether it's length, volume, mass, whatever this is representing, there are 7 sig figs. So we want to next identify where the natural decimal place is. The natural decimal place is right over here. It's not written, but the natural decimal place is right over here. And then we need to decide where is the natural decimal place going to move once it's shown in scientific notation. So we want to have one number in front of the decimal. We're going to have this number in front of the decimal. We are going to move our decimal place there. So next we're going to count how many times it takes to move the decimal from here to there. And watch the decimal move. We're going to count 1, 2, 3, 4, 5, 6 times. So the decimal moves 6 times. And then we are going to now show this number using scientific notation. I have 1.006051 times 10 to the 6th power because it moves 6 times. Now, you might be wondering, why did I have to write the entire thing? The entire number has to be written in front of the multiplication symbol because in chemistry with measurements, we have to make sure to retain the number of significant figures. There are 7 significant figures in the original number, so up here, we need to also have 7 significant figures in our scientific notation representation. It's not always going to have the same number of sig figs as written digits, and I'll show you that in another example. So let's go ahead to the next. By the way, what this actually means is we have 1.006051 times 10 to the 6th power because this is 1.006051 times 6. I'm sorry, times 10, times 10, times 10, times 10, times 10, times 10. And that each time you multiply it by 10, the decimal moves over. So the values are exactly the same. The meaning of these measurements are exactly the same. All right, so here's my next example. I have 0.0052300. I need to know how to count significant figures. And I wish I hadn't clicked too fast to that, but there are 5 significant figures in this measurement. We're going to assume these are all measurements. So the 5 significant figures are right here. 1, 2, 3, 4, 5. Remember the rule. Any leading zeros are not significant. So any leading zeros are not significant. And trailing zeros are only significant if there's a decimal somewhere in the number. So these are my 5 sig figs. So the natural decimal place is right over here according to the original problem. And we need to move our decimal place so we only have one number in front of it. Imagine where you are going to move the decimal place now. And I hope you imagine this spot right over here. We're going to now count how many times it's going to take to move the decimal from there to there. And here we go. 1, 2, 3 times. And now what we're going to do is we're going to take these 5 sig figs and we're going to use them for the scientific notation. These zeros are not significant to the measurement, therefore they are not represented in the scientific notation. I have 5.2300 because these zeros are significant. They have to stay with the scientific notation. And we have times 10 to the negative 3 because we move the decimal over 1, 2, 3 times. Now this time it's negative because it's like saying 5.2300 divided by 10, divided by 10, divided by 10. It's the same concept there that you've learned in math class, I don't know, whenever you learned about scientific notation the first time. So anytime you look at the original value of the number, if the original value of the number is less than 1, that is a great sign for you to make sure your exponent is a negative exponent. So go ahead and hit pause on this video when you're ready. Practice these examples out and just make sure you're keeping the same number of sig figs. When you're ready to keep watching, then keep watching. So here are the answers for these practice problems. First thing I want to recognize is that the first one only has one sig fig. So my scientific notation is only going to have one sig fig. To get to my scientific notation, I need to move my decimal place from here to here. And we move it 1, 2, 3, 4 times, 6 times 10 to the 4. No decimal place necessary. But if you had 6 with a decimal place, that's okay. It's just not necessary. In this case, I have 2 sig figs, 2 significant figures, because there is a decimal present. I'm only going to move the decimal place over once. And I have 2.0 times 10. You can have 10 to the first power, it doesn't matter. It works out the same way, but just times 10. For letter C, I'm going to move my decimal place from here to here. And it moves over 1, 2, 3 times. So 4.004 times 10 to the third power. And finally, for the last question, I'm going to move my decimal place from here to here. And I'm going to move it over 1, 2 times, but I look at the original value. The original value is less than 1, so I know I'm going to have a negative 2 as an exponent. So when you're trying to decide if it's a positive exponent or a negative exponent, look back at the original value of the number. If the original value of the number is positive, then go ahead and make that exponent positive. If the original value is negative, then that exponent should be negative. All right, so we're going to now convert this number into scientific notation. Just remember to keep in mind the rules of significant figures. However many significant figures you have in the original value, you must carry over to the scientific notation value. In this number, there's no decimal. So all of these trailing zeros are not significant. I have 4 sig figs right here. Here are my 4 sig figs. And I'm going to move the decimal over from here to there. And it takes 1, 2, 3, 4, 5, 6, 7, 8 movements, 8 times to move the decimal over. And I have 1.005 times 10 to the third power. If you're not hitting pause to try these on your own, you definitely want to do that first, because remember, practice makes you better. And if you practice and you get it wrong, it's okay. You just learn from that mistake, and hopefully you won't make that same mistake again. In this number, I have 1, 2, 3, 4, 5, 6, 7 significant figures. I need to retain 7 significant figures in my answer, and the decimal is going to move from here to here. And we're going to move it 1, 2, 3, 4 times. So 3.085000 times 10 to the fourth power. If you didn't hit pause already to try to work this one out, I definitely would stop and think, how many sig figs are in this number? Maybe on your paper you underline the sig figs before you do anything, because when it comes to having a bunch of zeros in the front and on the end of a number, the sig fig part gets confusing. Scientific notation's not hard. You've learned this before. The part that's hard is identifying the number of sig figs. So hopefully you identified this number as having 6 sig figs. Here are the 6. 1, 2, 3, 4, 5, 6. And when you move your decimal, you're moving it from here to here. It's going to move over 1, 2, 3, 4, 5 times. We have 1.02000 times 10 to the negative fifth power. Now, on a multiple choice test, I would probably have an option that was 1.02 times 10 to the negative fifth power as a distractor answer, because that would not be the same as this. When we have measurements, and we're assuming these are all measurements, when you have measurements, you must consider significant figures. The reason we are keeping these zeros in this number and not these zeros is because these zeros at the end of the number are significant to the original measurement. Whatever was being measured, those zeros have some significance in the measurement. These zeros, not so much. They were probably part of some sort of estimation, therefore they are not kept in the scientific notation. So we're going to go backwards now. If you understood how to do scientific notation up to this point so far, then this part should be easy peasy for you. So we are going to now convert to standard form or decimal form. That's all the same thing. These are the rules, but I like to work from examples. So just make sure you have these copied into your note packets, and then I'm going to go through the rules through an example. If I have 2.48 times 10 to the fifth power, and I'm going to convert this to standard form, the times 10 to the fifth power tell me I'm going to take my decimal place and I'm going to move it over 5 times. And when I move it over 5 times, I'm trying to create a large number because it's a positive 5 exponent. If it was a negative 5 exponent, I'd move it to the left and create a small number. So I'm going to move it over 1, 2, 3, 4, 5 times. And here's my decimal sliding over. And now we have to think, what are we going to do with all these extra spaces? We want to make sure the value stays the same. We can't just leave it as 248 because that's not the same thing as this. We're going to fill it in with zeros. But now you got to ask yourself, do I keep the decimal or do I take it away? We need to make sure we keep the same number of sig figs in the scientific notation versus the long form, so I'm going to take it away. This number now has 1, 2, 3 sig figs, but it still retains the value of 248,000, just like what this scientific notation represents. So there's your final answer. I don't want you guys to memorize rules like if it's positive, move to the right. If it's negative, move to the left. Avoid memorizing those rules because the rules actually flip. If you're memorizing move to the right when it's positive, well, how do you take your long form number and make a positive exponent? You're moving it to the left. So you're doing the opposite, and I don't want you guys to memorize a rule and, it's the backwards from what you're trying to use it for. So just remember, if it's a positive exponent, the original value must have been greater than 1. It's a large value. If you haven't, hit pause, and if you want to, hit pause and try this example out, and then keep watching to check your answer. I have 7.18 times 10 to the negative 6th power. The negative 6 is an indication that we're going to create a small number, and we're going to move that decimal point over to the left because we're trying to create a small number. So let's move it over 6 times. 1, 2, 3, 4, 5, 6. There's my decimal sliding over. I'm going to fill all of these spaces with zeros now. And so when I am trying to finish off, if I want to finish off the representation of this number, I do want to keep all these zeros in front. They're not going to affect the number of sig figs. I am going to be proper and put a 0 in front of the decimal. That way your reader knows for sure there's a decimal there and not just a speckle on your paper. It's not going to make a difference if you leave the decimal off or not in front. You leave the 0 in front of the decimal off or not, but it is proper to do so. I would encourage you to put that 0 in front of the decimal. In this value, this is the same value as this in the measurement, and we still have 3 sig figs and 3 sig figs. All right, so last little topic here related to scientific notation. I hope you have a calculator, and if you do not have a calculator, then I'm going to show you how to use the scientific calculator on your computers or, on your laptops. You can also download a scientific calculator app on your phones or on your tablets, and I just want to warn you that the button order is going to be a little bit different, but you can make it work. So we have this button on our calculator, the EE or the EXP button. Whenever we're using scientific notation, you're going to use one of these buttons to replace the times 10 to the exponent. Okay, so check your calculator right now. Just make sure you can locate this button. I've seen some newer calculators represent it this way, but typically you'll see like an EE or EXP button. We do not want to type in times 10 to the caret, especially on like our graphing calculators. We want to try to find this button because it shifts your answers by one decimal place one way or the other, like 10% of the time. So we want to be correct 100% of the time. So for example, on your calculators, if you wanted to type in 4.22 times 10 to the 23, you would type in 4.22, find that EE or EXP button, and then you hit 23. There's no times 10, there's no caret button. This is exactly how you would type the scientific notation into your calculators. So I'm just going to show you real quick what the scientific notation button might look like on a computer calculator. So here's your computer calculator. Now typically it's going to be in your standard form, but what you can do is you can click over here. You can actually change it to scientific notation form, and here's that button I was referring to, that EXP button. So you can type in 4.22, then I'm going to hit an EXP, and that creates my scientific notation right there, and then 23. And so what that does, when I hit enter, this particular calculator actually can fit all of these numbers. It's not typical that a calculator can fit 23 numbers in there, so you won't see the full effect of the number on most calculators. It'll just continue to show you scientific notation if the number's too big to fit in the calculator. So that's how you can change your computer calculator into scientific notation mode. So now I'm going to go back to PowerPoint. So this is just a little tutorial here. If you want to go ahead and try this out, we want to just practice. Type in 2.50, hit that EE or EXP button, then 4, then multiply it by 2.51, hit that EE button again or EXP, and then hit 5. This is what your calculator might look like, or yeah, and then this is the answer you should get. If your answer in your calculator shows like 6.275 times 10 to the 9th, that's okay too. This is a rounded answer, so this is what your calculator might show, 6.275 times 10 to the 9th power, or something like this. Just depends on how many digits your calculator can hold. But here I did not type in a times E. I didn't type in any carets. If you do not have this number in your calculator from this practice, or this number in your calculator for practice, you are typing it in incorrectly and you want to reevaluate that. So let's just practice. I'm going to go ahead and put the answers up here. Hit pause, try this out in your calculator, and hit pause to make sure that you can get these. If you're off by 1 decimal place, you're typing it in wrong. So if you're typing it in wrong, here's how to correctly type it in. You have 7.89. Actually, I'm going to pull up my scientific calculator again on my computer so you can see the calculation here for this. Hit clear. I have 7.89 right here. I'm going to hit my EXP button, and then I have 24. Notice I did not hit times EXP. I didn't hit my caret button, none of that. I'm going to go ahead and hit the division sign now, and I'm going to divide by this. 6.02, hit my EXP button again, and then 23. So when I hit enter, I get 13.1. I have ... here because I didn't really need to write in all of this number. And so that is how we are going to use our calculators to calculate scientific notation. Go ahead and practice this one without, if you haven't already, because some people just assume they get it. And, you know, when you assume that you get it and you don't perform on the test, you're mad at yourself later for not taking the moment to practice when you should have, when you had that opportunity. So I'm going to show you how I would type this one in now. 63.78 times, and then I'm going to put this in scientific notation, 1.56. I'm going to hit my EXP button. I'm going to hit 3 negative. Sometimes with the calculators, you have to put buttons out of order. My blue calculators, my TI-X2S, 30X2S models in our classroom, you type everything in order, and that's fine. But on some scientific calculator apps or some of the older model calculators, you have to be careful with when you hit the negative button. So that's why I did that in that odd order. You can rewind it and watch it again if you don't know what I'm talking about when I say in odd order. When I hit the equal button, I get the value that I see on the PowerPoint. So that's a good sign. If you're getting a number that's shifted over by 1 decimal place, that means you're doing it wrong. So continue to rewind the video, rewatch how to properly type it in, because I don't want a silly multiplication symbol to be the reason you get a question wrong on a test, okay? So the next part of the PowerPoint is just a practice section. This is the last little section that you're going to do on your own to finish up this video lesson. So go ahead and just hit pause as you practice, and then just keep watching if you're ready to see the answers. Here are the answers, and you might even want to just have these up while you're practicing. Just type it in, check your answer. 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 And if you're off by 1 decimal place, that's not okay. Rewind the video and make sure you can type it in correctly. All right, so that's the end of our video lesson for this time around. Now you can do the set that corresponds to the scientific notation section. And I would just make sure that when you're doing your study packet set, realize that there's a good chance there are more questions on the next page. All right, thanks, and I'll see y'all soon.